All right, so this is a fairly basic rundown of some complex numbers or imaginary number type problems that you might expect to see on a quiz, or just that you should be competent with before moving forward. So I went ahead and I did a little cheat sheet for myself up here with some basic definitions. So first off, the most basic definition is simply that I is equal to the square root of -1. Then we go ahead and we do I squared. Well, I squared, if I is equal to the square root of -1, then I squared is equal to the square root of -1 squared. Well, if we do that, the square roots will cancel out and we're left with -1. So I squared is equal to -1. Moving forward, I can do I cubed. Well, I cubed, based off of my, my exponent rules, is just I squared times I. Well, I squared is -1. I is the square root of -1, so I cubed must equal -1, or just negative square root -1. I to the fourth, I can rewrite that as I squared squared. Again, we'd have two I squareds times each other, which would give us 4 I squareds times each other total. That is simply -1 squared, which is 1. Okay. And so a lot of these problems are going to ask us to write things in standard form for a complex number. And standard form is simply A plus BI, where both A and B are real numbers. So this is the real part, and this is the imaginary part. So basically you're just kind of keeping them both separate, but in the same statement. All right, so for number 1, this is an example where you go through and you just see if you can simplify it or anything. Basically, I is the most simple, and you don't really need to have I squared, I cubed, I to the fourth. After I to the fourth, they actually just repeat, and we can write them all in terms of I. So I'm trying to get it in this form here. Well, I see I have 5I. That seems okay because I can have BI. That's acceptable. But then I have this I squared. Well, I look up to my cheat sheet, and even if you don't have the cheat sheet, just think square root of -1 times square root of -1. Well, I can replace this with what it's equal to, -1. Okay. Plus 5I. Well, that's looking much better. I'm going to go ahead and rearrange it as -1 plus 5I. But as you can see here, that is more than acceptable. Now another example, and I forgot to put this up here, would be if you had something like I to the 22nd. Well, moving forward, you're always going to want to look at ways to simplify things based off of some other things you know. So I know that every 4 I's I can group together is just 1. So I'm always going to try to group up as many of those 4's as I can, because then I can just kind of get rid of them. So I know that I can get I to the fourth. Well, I can have 5 groups of those. If I have 5 groups of I to the fourth, then I have 20 of them. That leaves 2 left over. Well, this I know is actually just equal to 1, so now I have 1 times I squared. Well, I squared is none other than -1, so this would just be -1. This would be an example of, again, breaking it down and simplifying. All right, moving on to number 2, here would be another common example, and you can think of this a lot like combining like terms. But before we do that, we still don't like this negative in the square root. Okay? So what we're going to do is we're going to go ahead and reduce these square roots down as much as possible. Okay? So I'm going to keep my -1 there, plus, well, the square root of -8, I can rewrite as the square root of -1. Now, I also notice that 8 has a perfect square in it. One of 8's factors is 4, so I'm going to go ahead and factor that out as well. Square root of 4 times the square root of 2. Now, if we go through and multiply those back out, -1 times 4 times 2 gets us back to the square root of -8. So, since this is equal to these, I can replace it with it. Now I'm going to add 8 minus, and I'm going to do the same thing here. I'm going to pull out that -1, And then I'm going to look for any perfect squares that I might have in this particular one. Well, hopefully you notice that, well, 25 goes into that 2 times. 25 is most definitely a perfect square. 25 times 2. And again, I'm going to multiply it back out to make sure I can get back to my original expression. Negative 1 times 25 times 2 will give me negative 50. So I know I'm in good shape. Now I can go ahead and simplify. Okay, so here I have negative 1 plus, well, this is just I. This right here is 2. Square root of 2 is going to stay as square root 2. Okay. Plus 8 minus, well, again, this is I. This becomes 5, and this stays as square root 2. Now, this is a trick that you'll see in a lot of problems like this. Now we have square root 2 and square root 2. We're actually going to be able to combine some of this together. But we don't want to get too ahead of ourselves, so let's go ahead and simplify a little bit farther. And I needed an extra parenthesis here. Okay. And if we do that, what we're going to end up finding, oh, no, I didn't. Well, whatever. That doesn't matter. All right, if we continue on, what we're going to end up finding is that we have negative 1, okay, plus 2i. That's the preferred way to write it, is to write basically 2 is the coefficient, and we have I square root 2 plus, and I'm getting rid of the parentheses. I don't think they're necessary anymore. 8 minus 5i square root 2. Well, now, this is what I was talking about. We're going to combine like terms. So I'm going to regroup these, and I'm going to combine together the negative 1 and the 8. I'm going to group those together, negative 1 plus 8. And then I'm going to go ahead and group together the imaginary parts. Now, grouping those together, I find that that is in fact equal to, plus, I'm adding 2i square root 2 minus 5i square root 2. Okay. Well, if I combine these together, I just get 7 plus, well, I have all my i's together, which is exactly what I want based off of my standard form of a complex number. Well, I have both of these have a base, and you can almost treat that as a variable of square root 2. So here I have 2i's, or 2i square root 2's, and here I have 5i square root 2's. I'm subtracting the 5i square root 2, so I'm going to wind up with negative 3i square root 2's left over. And you can go ahead and turn that into a subtraction problem if you choose to, but it is absolutely not necessary. Okay, now moving right along to the next one. This one's more of a definition than anything else. And when I think complex conjugate, what I end up thinking is that you're basically creating a difference of sums. Now, that might sound a little bit strange, but it's very similar to when we talked about difference of squares. So the complex conjugate to this, if we have 7 minus 5i, well, then the complex conjugate is just going to be 7 plus 5i. Now, the use of this is that if we multiply a complex number times its complex conjugate, we get a very similar result to what we get when we do a difference of squares. So, in fact, I'm going to go ahead and scrap this problem down here because it's about the same as what I'm going to do here. So if we FOIL this out, we get, first is 7 times 7, which is 49. Outside, well, 7 times 5i will give us positive 35i. Inside, well, here I have negative 5i times 7, and that's going to give me negative 35i. And then we have last, which is negative 5i times 5i, which is going to be minus 25i squared. Well, one thing I can immediately see is I have a positive 35i here and a negative 35i there. Those are going to cancel. The 49 is just going to stay the same. And in fact, I look here, And what ends up happening? Well, I have negative 25. That's just going to stay the same. But I know I squared, well, that's actually just equal to negative 1. So I can rewrite this as negative 25 times negative 1. Well, negative 25 times negative 1, I'm now going to have 49 plus 25. And that is, in fact, equal to, can't do that at the top of my head, it's 74. Now, when you will use this, if you recall, is if you have, for example, you had something like 3 over 7 minus 5i. Well, in the end, what we really have here is we have a square root on the bottom. Well, you should have learned in Algebra 2 that we don't generally like to have a square root on the bottom. So what you can do is multiply both top and bottom by the complex conjugate, or 7 plus 5i, and in fact this is really just the conjugate, okay, that you learned when you were dealing with radicals. 7 plus 5i, well, this ends up being 21 plus 15i on the top, and on the bottom, well, we just found out that this is equal to 74. Well, I can distribute that 74 to both terms, so I can actually separate out fully my two my real and imaginary numbers, and I would get 21 over 74, okay, plus 15 over 74i. Okay, and that is an example of most of what you would need to do, at least in the immediate future, with complex numbers.